Hi everyone, I have three reactions to talk about in this video dealing with carboxylic acid derivatives. Those three reactions are going to be ester saponification, ester plus Grignard, and acid chloride plus Gilman. None of these reactions are really interconversion reactions between the derivatives. As a reminder, from the first video, we have this ski slope. I think we've taken care of all of these reactions, actually, right? We took care of all the hydrolysis, the ones in red. We took care of all the interconversions as we go from a more reactive derivative to a less reactive derivative, meaning that we always go downhill. Yeah, so all the reds, the purples, and this SOCl2 was taken care of. But there are other reactions that are not shown here, in particular reactions dealing with esters. Okay. This is reaction 6F. It has a special name, saponification. Saponification, if you know your French, let me make sure I know my French. What's the French word? Savon. That equals soap. So actually, the process of saponification is how people made soap in colonial America, in Egyptian times. What they did was they take animal fat, which is an ester. Let's take this ester here. Animal fat that typically has a long alkyl chain, and we'll make it an ester that looks like this. Next is we're going to add strong base. Actually, before we do that, it's a type of hydrolysis, but it's base-mediated. And the base we're going to use is NaOH and some heat. What happens here is we're going to, like I said, hydrolyze. Find your dot. We're going to cut right here. And we're going to add water. Okay, hydrolysis is you add water to lyse the molecule. You can imagine that the water will come in here, and we're going to kick out this group here, which will ultimately become an alcohol. Now, the thing is, with hydrolysis, when we did acid hydrolysis of an ester, what were the two products? The two products were carboxylic acid and an alcohol. The thing is, actually, let me draw this a little bit more clear. The thing is, you have a carboxylic acid that's in the presence of base. You're going to do an acid-base reaction, and you can't stop it from happening. You don't make the carboxylic acid, you actually make the carboxylate. And if you want to have a counterion, you could put sodium as the counterion. Don't forget that. So your two products are going to be the carboxylate and the alcohol. Why is this saponification? Okay, this is how to make soap because this is a detergent. And when you have a charged head or at the start of the molecule, and I'll just put a negative here, and you have a very long hydrophobic hydrocarbon tail, and you have that. Well, this is not very water soluble. So what's going to happen is it's going to form what's called a micelle. And your molecules are going to aggregate like this. Okay, imagine the sphere, okay, all the way around, 3 dimensions. I'll finish it up actually, like this. Okay, but it's all filled with these detergent molecules. Well, outside it's water soluble, attracted to water, but inside it's very, we call it hydrophobic, and it traps a lot of grease. thick molecules that are nonpolar. So a good soap is a combination of a charged hydrophilic head and a long hydrophobic tail to be able to carry out the grease, but that's not good enough. You can't just have detergent lop onto like a dirty shirt. You got to have some water solubility so the water could carry it out with the detergent water, with the bath water. Okay, let me show you the mechanism. Oh, by the way, in terms of doing this in practice to make soap, you have your vegetable oil or animal fat, and you have a base. And typically you could use NaOH, but also you could use KOH, and that's called lye. So you might have seen recipes where you take vegetable oil or animal fat, you hydrolyze it by heating it up in lye, and you wait, I don't know, a day or 2 days, and it will start to solidify to give you a soap, a bar soap. I want you to know the mechanism, and yeah, we'll just use the same molecule. It's called base-mediated, not base-catalyzed. That's because the base is not acting like a catalyst. A catalyst means that it will do its job, but you don't actually consume it. So you only need a little bit of catalyst to do the reaction. We don't need a little bit of OH minus. We need a lot of OH minus. We need 1 molecule of NaOH for every molecule of vegetable oil because that's the OH right there. So we need at least 1 equivalent. It's not catalysis. So where am I going to write that? I'll write it up here. Saponification is base-mediated hydrolysis. Okay, very easy. We have the OH minus. Oh, it's anion. So this is a pretty good base, but also it's a very good nucleophile. And you know what happens with nucleophiles when you have these derivatives? The nucleophile is attracted to the partial positive carbon. And what do you make? It begins with a T. You make some type of intermediate called the tetrahedral intermediate. Oh, good. It's neutral already. Very easy. We don't have to worry about deprotonating yet. Caveat. We do what we normally do is we go ahead and when we have an opportunity to collapse a tetrahedral intermediate to kick out the leaving group. You see there are common themes for a lot of these mechanisms that deal with derivatives. I'll go down here. What do we have? Double check the number of carbons so I don't miss any. But I released an O ethoxide, O ethyl minus. Minus. You can't keep these separate. Okay, they're in the same pot. So once you make this, you have an acidic functionality and a pretty good base. The carboxylic acid is more acidic than the alcohol. So the H is going to be transferred, the proton. And your main products are ultimately the carboxylate, which I mentioned, at the beginning, and the alcohol neutral. You can think of this as an acid-base reaction. Equilibrium favors the weaker acid. The carboxylic acid is pKa of 5. The alcohol is pKa of around 16. You favor the weaker acid, so these are your 2 final products. Okay, saponification. Not bad. Let me just label this so you don't forget. This is called a micelle. You look this up on Google, you'll see 3-dimensional representations of a micelle. They're pretty cool. Okay, next is ester plus Grignard. Ester plus Grignard. Reaction 6G. Ester plus Grignard reagent. We could also use, as usual, organolithium, but I'm partial to Grignards. You know what a Grignard does? A Grignard adds to an aldehyde or ketone, or we saw carbon dioxide or an epoxide, right? It attacks the carbon that is bonded to an oxygen. In this case, let's use a simpler ester. And let's use a Grignard that we can track. The Grignard I want to use is going to be maybe, let's make it 4 carbons, MGBr. You know with a Grignard, you're typically going to have to protonate an alkoxide. Okay. Second reaction is water, acidic water. Here's your carbon that you're going to attack. We'll get to the mechanism because I think it's important to understand this fully. But we're going to add the alkyl group of the Grignard twice. When you have ester plus Grignard, think of it as add the Grignard twice. You are going to assume that this is an excess. If there's nothing here that says 1 equivalent, 2 equivalents, or 1 mole or 2 moles, you're going to assume that it's an excess. And if the intermediate that you make is still reactive to that reagent, you're going to do it again. Okay. We're going to add it twice to this dot. We have a very good leaving group, right? This is the leaving group. Maybe not a great leaving group, but for all of these derivatives, when you do a reaction, you typically kick out the leaving group. So we're not going to see this O-methyl in the main product. What are we going to see is this dot. The carbonyl group becomes an OH, and we're adding the Grignard twice, so 1, 2, 3, 4, 1, 2, 3, 4. Whenever you see a tertiary alcohol, and 2 of the groups are the same, then you can make that tertiary alcohol using an ester plus Grignard. And you could tell that, well, we'll look at the mechanism, but later on you'll see that these 2 groups came from the Grignard reagent. Okay. Just a little note. If you can use Grignard, you could also use organolithium. Yeah. Let me show you that mechanism. How are we able to add that alkyl group twice? We start out with the ester. How do we draw an arrow from the Grignard reagent? Here's your Grignard reagent. Remember, it's this carbon that's nucleophilic, the carbon next to the metal. But to show the connection between that carbon and the carbon of the ester, you start from the bond and you attack. What kind of intermediate are we going to make? You guessed it, we're making the tetrahedral intermediate. O minus, leaving group, and the Grignard reagent, or the alkyl of the Grignard reagent that we added. If you're wondering what happened to the MGBr, we broke the bond between the magnesium and the carbon, so that MGBr is just hanging out. It could act as the counterion of the alkoxide. And that It's going to happen. You're going to make a salt. Now, normally with a Grignard reaction, you would just protonate this oxygen and you're done. You get an alcohol. But what do we do usually? After the tetrahedral intermediate, you collapse this lone pair to make the double bond again, and you kick out the leaving group. We've done that. I mean, we did that with saponification, right? See, after the attack, the tetrahedral intermediate reforms the double bond, kicks out the leaving group, and that's why we have the C double bond oxygen. We're going to have the same thing. We're going to have it come back, the C double bond oxygen, with now this alkyl group from the Grignard, plus we got rid of this leaving group. I'll just put CH3. That just hangs out. Okay, nothing else is going to happen. But what did we make? In the process of this reaction, we made a ketone. And you know that ketones and Grignard reagents are reactive to each other. The Grignard's going to attack this ketone. We can't say stop to the reaction. We can't say you made the ketone, don't react anymore. Because if there's any Grignard reagent available, and there is, we're going to assume that there's excess, you are going to attack, again, that carbonyl group and create the tetrahedral intermediate. You might wonder, well, can't we control this using exactly one equivalent of the Grignard and say, after all the Grignard is consumed to make the ketone, there's no more Grignard to do this reaction here? In theory, that sounds good, in theory. But it doesn't work like that in theory, because the ketone actually is more reactive than the ester. And not all of this happens at the same time. So when you make the ketone, if there's any Grignard reagent that you're hoping to react with more of the ester, it's not. It's going to more likely react with the ketone. There's no way that we could run a reaction where we say, all at the same time, convert all of the ester to the intermediate. Okay. It happens, it doesn't happen instantaneously. So the fact of the matter is, if you had exactly one equivalent at magnesium or butyl magnesium bromide, exactly one equivalent, you'll have unreacted ester because some equivalents, some percentage of the Grignard reagent will react with the ketone immediately, much more quicker than the ester. Now we're here. There's no leaving group, so we can't remake the double bond. We just have to protonate. You see, I didn't mention it when I drew it. See, I added the second alkyl group due to the second Grignard reagent. And we have this. Our final product looks like this, just like we had on the previous page. Man, messed up. OH, sorry about that. And then two alkyl groups that are identical. This is a mechanism. We did create water, so let me just put that here. Is there anything else I missed? If you want to do the counter ion, again, MgBr. I think we're good. If you think about, what happens with this, you're all in the same pot, and then you could probably protonate this also, this methoxide with the water, acidic water, but no one really is interested in that piece that got kicked out. Good. 1, 2, 3, 4 steps to make the tertiary alcohol. What did we just do? Grignard plus ester gives you a tertiary alcohol. Before I do the last reaction of this video, let me give you a problem to work on at home. Here we have a tertiary alcohol. What are some ways we could make this? Before this video, we talked about ketones and Grignards. So we could probably make this via a Grignard plus ketone. Because we have two of the groups that are the same, normally you could make bond A, make bond B, make bond C, 3 different ways, Grignard plus ketone. But because this bond A and bond C are to the same group, those are identical reactions. I would say that there are two ways that you could use a Grignard and ketone to make this molecule. Can you come up with those two ways? Let me just double check if I'm right. Yeah, two ways. The other thing is, could you make this via a Grignard plus epoxide? And that's a little bit harder to analyze in my head. Let me double check. That's one way. There's one way. There's one combination of Grignard plus epoxide that will give this molecule. If you come up with a second way, let me know. But I think there's only one way. I'm saying there's only one way. But what about what we just learned? Ester plus Grignard. We have two of the same groups. So we could do Grignard plus ester. And there's one way for that. I'll probably make this a practice problem for this video. So those of you who are in my class, watch out for that. Let me take care of the last reaction, reaction 6G. Oh no, 6H. This one also is kind of tricky, and I'm not going to show you the mechanism for this. Acid chloride. Do you remember what a Gilman reagent looks like? Remember, the Gilman reagent has those two R groups connected to CuLi. I'm going to give away the ending. You're making a ketone. Okay, strange. Really strange. Why? Well, maybe because, last time we formed the ketone here, it still kept reacting. But ketones and Gilmans in this reaction don't react with each other. Okay? And I teach my class only to use the Gilman to react with a alkyl halide, not a ketone. But here's the second way that we could use a Gilman reagent. Let's take this acid chloride. This one here. And the Gilman. Let's just do an ethyl Gilman. The form again is this. And you don't need anything else. Remember for the Gilman that you only add one of the alkyl groups, even though there are two of them. And you usually add it to an alkyl halide to make a hydrocarbon. Here, what's going to happen is all you're going to do is make the ketone. So what ketone do you think I'm making? You definitely have this part on the left. You definitely have this carbonyl group for the ketone. And really, the other R group for the ketone will match what's in the parentheses. Just put an ethyl group here. That's it. I'm not going to show you the mechanism. I could ask you maybe how to make this ketone. This will be interesting. That. There are many ways to make this ketone, right? You could take an alcohol and oxidize it to the ketone. You could do a Grignard reaction to get the alcohol, then oxidize it. There's actually not a lot of ways to make this ketone. But here I'm going to force you to make a ketone via acid chloride plus Gilman. It is your task to figure out what that Gilman reagent looks like and what the acid chloride looks like. I'll put this on the practice problems for this video. Why don't I try to do this for you here, and you could test it yourself. I need an acid chloride and I need a Gilman. Alright, let's see if I could do this one. I'll make the acid chloride the stuff on the left. And the Gilman has 1, 2, 3, 4, 5 carbons, and your point of attachment is right here. Right there. So, within the parentheses, I need to have 5 carbons. Okay, so don't put the parentheses here, because there will be only 4 carbons inside. You have to draw the parentheses and extend out of the parentheses. That should give us a good Gilman reagent to add these 5 carbons. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Adding to this dot, adding to this dot. Okay. That's good. We could do that. But we could also look at it as making the bond on the left, I believe. Let's see what that does. You know, this is a benzene ring. I'll draw it out first, and then I'll show you the abbreviation. So yes, you have to fit the benzene ring in the parentheses and make the Gilman like that. And that carbon of the ring is going to attack and attach to this carbon of the acid chloride. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Another way that you could write this, if you don't want to draw it out, a benzene ring, when it acts as a substituent, is called phenyl. Literally, you could write pH 2 phenyl groups, copper lithium. That's a phenyl Gilman, so to speak. Okay. All right. Very interesting way to make a ketone. You don't need to know the mechanism if you are in my class. Okay. All right, I think I'm going to end the video there. Those are the main reactions that I want my class to know, all the way up to reaction 6H. There are several more reactions in your textbook that you could read about, but for our class, let's just have those reactions up to H. Okay. Maybe in class or maybe in a separate video after this, we could try, what can we try? We could try roadmaps. We could try recategorizing. I'll tell you this, if I could find it. The way that we talked about these reactions, how we categorize them. Look at our first reaction from the second video, reaction A, hydrolysis. I said we're going to do hydrolysis, and I listed all the derivatives and did hydrolysis. So when I taught this, I categorized them in terms of the type of reaction. But what can you do to sort of rehash or try to organize this a little bit differently in your brain? Why don't you go through all of these reactions, A through H, and instead of categorizing them by reaction type, categorize them by starting material. So now what you could do is you could have a roadmap, and your roadmap can look like this. Well, heck, we could have a note card. Your note roadmap could look like this, where you have an acid chloride in the middle, and you could do hydrolysis. We just did acid chloride plus Gilman. You could do acid chloride plus amine, acid chloride plus alcohol. Acid chloride, I think maybe, I'm not sure, I said hydrolysis. Do that for each of your 4 derivatives. That's a great way to reorganize your thoughts and to get everything onto a note card for one functional group, one class of molecule.